Yeah,
All
we're
right,
getting
let's
there.
get started. So hello and welcome to for Australia, the 7 p.m. session. This is labeled as the Mediterranean B session. So we'll have 3 talks in this session. They will all be 40 minutes plus 5 minutes questions. And so I will give a 5-minute warning. So you'll have to forgive the interruption speakers. I'll give a 5-minute warning after 35 minutes. And then at question time, and then if you want to eat into your question time, you can, but we'll be moving on to the next talk after 45 minutes. So with that said, the first speaker is Akira Furusawa from the University of Tokyo, and he'll be speaking about large-scale quantum computing with quantum teleportation. Take it away, Akira.
Okay. Okay. All right. My name is Akira Furusawa. First of all, I'd like to thank organizers for giving me the chance to be here. The title of my talk is Large-Scale Quantum Computing with Quantum Teleportation, which is my favorite. Let me introduce myself. I was a member of this quick project more than 20 years ago. In that, I'm very young here. And in that project, Jeff Kimball was my boss, and Daniel Gottesman and John Preskill. And even Alexei Kitaev joined this project next year. And I did quantum teleportation experiment in that project. Since then, I have been working on quantum teleportation for more than 20 years. And I'm a windsurfer. There are a lot of collaborators. This is my group at the University of Tokyo, and there are so many senior collaborators, including Hidehiro Yonezawa, Shota Yokoyama, and Nikme Nikuchi, and Ralph Alexander, and of course, some Australians, Tim Ralph, Howard Wiseman, so on. And my Bible is this GKP paper. Of course, we were colleagues. And so from the very beginning, I was thinking about using this GKP qubits like this. And my encoding scheme of GKP qubits are something like this. We use quadrature amplitude modulation, nowadays called QAM, for GKP qubits. And this QAM is very popular these days for coherent communication. And here, AM axis. AM means AM radio, amplitude modulation. And here is frequency modulation, FM. I'm old enough to understand AM radio and FM radio. But younger people might not be able to understand AM radio and FM radio. So this is kind of boundary between younger people and old people. But I'm very old, so I love AM and FM picture. And phase space is represented by using combination of this AM and FM. And this AM and FM is like position and momentum, of course, they are orthogonal. And we can define this annihilation operator like this. And it can be regarded as complex amplitude of electromagnetic field. And X and P has this commutation relationship. So it can be regarded as position and momentum. And by using this framework, we encode GKP qubit. And by using GKP qubit, we can make operations with continuous variable fashion. For example, this is a logical zero of GKP qubit. And for bit flip operation, we can use X displacement. So X displacement by pi, square root pi, makes this state to like this. Similarly, by using P displacement, I mean displacement in this direction makes Pauli Z operation, phase flip. And 90 degree rotation in phase space correspond to Hadamard transformation like this. So, I mean, this can be transformed by using a 90 degree rotation in phase space. And also to make a universal one-mode Clifford operation, one-bit Clifford operation, we need this phase gate. And for that purpose, first we make 45 degree rotation, and then displacement in this direction by square root pi, and then make squeezing in this direction. So we can get this one. So by using Gaussian operations, we can make this phase operation. So this is universal Clifford operations. And for universal quantum computation, we need this T gate, pi over 8 gate, and of course C0 gate. But for us, C0 gate is very easy. So the most difficult part is this pi over 8 gate. And there are two types of the schemes to realize this pi over 8 gate. One is the way with cubic phase gate. And another way is using GKP magic state. But in both cases, we use gate teleportation. And actually, the difference between this path and this path is just ancillary input state. So for cubic phase gate, we need this ancillary input. And for magic state path, we need this magic state. And we can use the same gate teleportation setup. So the difference is very tiny. And to make large-scale quantum computation, we use this setup. And it is universal. And it is large-scale and universal and fault tolerant. And even more actually. We use homodyne measurement like this, and every measurement homodyne measurements, but this one can be replaced by using optical parametric amplifier. It was originally proposed by Tim Ralph. And in that case, we can make all operation can be done by using all optical scheme. And importantly, optical carrier frequency is more than 100 terahertz. So we can realize 10 terahertz clock frequency. And with this quantum computer, we don't have to have Shor's algorithm. Classical algorithm itself is very fast. I'd like to explain the scheme of our quantum computing. Everybody knows circuit model, but we are using this measurement-based model. And these days, I call it as a quantum lookup table because there are two types of computational model in a classical computer. One is, of course, gate model, and another one is lookup table. That is table of input-output relationship. And in our case, we use cluster state, which correspond to quantum lookup table. I mean, that is superposition of all input-output relationship. And by using measurement, we can select one of them. Of course, the measurement result is random. And to eliminate the randomness, we can make feed forward and select some particular operation. And this measurement and feed forward with this entanglement is pretty much the same as quantum teleportation, which is my favorite. That's why we are doing this one for more than 20 years. And this methodology is very powerful for flying qubits, actually. If we use flying qubits, there is no scalability, actually. Of course, flying qubits need real quantum circuit. Stationary qubit doesn't. Stationary qubits do not have to have real quantum circuit. Quantum computer is just just qubits. But in the case of flying qubits, we need real quantum circuit. So large-scale quantum computing needs large-scale optical setup. Even worse, there is no flexibility. I mean, some particular quantum circuit can compute some particular task. And if you want to change the task, you have to change the circuit. So that's why there is no scalability for quantum circuit model with flying qubits. But if we go to measurement-based model, we can solve all problems. For example, we can create ultra-large scale cluster state. even 7 years ago, we succeeded in 10,000 web packet. And 4 years ago, 1 million. Actually, that was unlimited. And the methodology is very simple. Two squeeze vacua are combined by using 50-50 beam splitter and making bipartite entanglement and delayed by a one-way packet and recombine here to weave a 1D cluster state. And we make measurement here and feed forward, feed forward, feed forward forever. And of course, it is input, output, input, output, input, output. So just 1D. And this is teleportation from here to here and here to here and here to here and here to here forever. And it can be extended to 2D like this. And we succeeded in creation of large-scale cluster state. And I'd like to explain the mechanism. First, we create a 1D cluster state, 2 lines of 1D cluster state like this, and then combine here and create 4-party entanglement. More precisely, we are working on web packets. So if we just these 4, it is entangled like this. And the next 4 is, of course, entangled, and so on. Then we have delay lines. Here is delayed by 1 web packet. And here, in this case, n equals 5, so 5 web packets. And then we have 2 50-50 beam splitter here. Then we make entanglement in these 4 web packets. So it becomes very messy. And it can be rearranged like this. And it is 2D. And more precisely, we are just using 4 squeeze vacua. So it is spiral like this. And to check this entanglement, we use so-called Furusawa criteria. We use 4 continuous variable version of stabilizers called nullifiers like this. It is non-classical correlation. So, for example, these 2 nullifiers, we can check this 6-party entanglement. And these cases correspond to time index. So just changing these time index, we can check these 6-party entanglement like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. And similarly, by using 2 nullifiers, we can check this 6-party entanglement. And again, changing time index, we can check this one and this one, this one. So in this direction. So overall, we can check overall 2D entanglement like this. And for that purpose, we need 4.5 dB of squeezing. And here is a experimental setup. We need 4 squeeze vacuum and 5 beam splitters and 2 delay lines and 4 homodynamic measurements. And this is a reality. 4 POs and many mirrors and beam splitters, but should be 5. And 2 delay line. One is just spatial delay line, and another one is fiber. And did the experiment, and we got all nullifiers, variances were below this 4.5 dB. And we declared the success of the generation of cluster state, 2D cluster state. Now, I'll talk about the operations. I mean, these operations. And we did phase space rotation and shear and squeezing by changing these local oscillator phases. And first example was quantum teleportation, which is my favorite. And here we used time domain multiplexing, of course. So this entangled pairs are coming to 50-50 beam split, and then this one, and so on. So we can regard this process like this, and here this ref and in, and 1 and 2 are entanglement. And of course, ref and in are also entangled. And this in is input for teleportation. Of course, we in 1 and 2 are entangled, and we have this type of non-classical correlation. And for teleportation, we set these local oscillators P and X. So X, P like this. And we make measurement. And we have beam splitter here and make measurement of P and X. So we have P and X, and the measurement result is MA and MB, and it is Bell measurement called Bell measurement course. We can create this type of non-classical correlation, which is entanglement. So this Bell measurement makes entanglement between this in and 1. And then this is the relationship by using this one. And with entanglement, we can neglect this part terms. And then by using measurement result, we can make feed forward. And we can eliminate or cancel out these terms. So now input and output are the same. That is teleportation experiment or identity operation. And we are using input like this, and we are teleporting this one. So if we succeeded in the teleportation, this one should appear here. So this ref and out should entangle again. So that's why it is called entanglement swapping. And for operations, we change local oscillator phases like this. And we can make this rotation and squeeze and rotation by using this measurement and feed forward. And more precisely, by using this local oscillator setup, we can make rotation. And like this, we can make shear. And like this, squeezing. And in the case of squeezing, this measurement becomes like this. Measurement result is like this. So we can make complicated entanglement. And then these equations can be modified like this. And again, we have a non-classical correlation here. So this term vanish. And by using measurement result and feed forward, we can cancel out these terms. Then we can make this matrix element, transfer matrix element. And we did that experiment. And we checked this transfer matrix by using entanglement. So again, this ref and in are entangled and 1 and 2 are entangled. So in and ref has this relationship, non-classical correlation. And of course, cross terms are not entangled. No correlation. Then we can estimate these matrix element by using these terms because we have disentanglement and disentanglement. So by using this entanglement, we can estimate this one, and by using this entanglement, we can estimate this one. And we did that experiment. For that purpose, we set local oscillators for operations set like this, and like this. And for reference, we check, we set local oscillators like this. And then this is the experimental results. This one, there is no correlation. So matrix element should be 0. And by using this slope, we can determine these elements. And again, here is 0. And overall, we got this result. For example, for phase rotation, these diamonds are experimental data, and these dashed lines correspond to theoretical curves. Very pretty much agree well each other. So we succeed in operations. Actually, it is Gaussian or Clifford universality for one input. And now we are coming to non-Gaussian or non-Clifford operation. And for that purpose, first of all, we tried a cubic phase gate with gate teleportation. At the moment, our ancillary input is just vacuum, and we have non-classical correlation, non-linear feed-forward for gate teleportation, and we made this crazy FPGA board, and we succeeded in non-linear feed-forward called dynamic squeezing gate, and overall performance of kind of classical gate teleportation is that we got this parabolic output. And of course, we are using this classical ancilla, so we don't have any wavy structure, but we have a cubic phase state like this. We can add wavy structure here. So we will put this cubic phase state here. And the important message here is that if we can prepare this magic state, we can make this operation with the same nonlinear feed forward. So in that sense, we are very close to the goal. And so the final problem, of course, should be creation of these non-Gaussian states. And for that purpose, we are now preparing a state synthesizer. Our state synthesizer is like this. Here is heralding generator, and we have quantum memory here. I mean, we have a shutter here. Here is OPO and a little bit higher pump. I mean, not parametric down conversion, but higher pump. I mean, in that case, we make two-mode squeeze vacuum. And two-mode squeeze vacuum has this type of 1, 1, 2, 2, 3, 3 types correlations. Of course, we have quadrilateral correlation like entanglement, but here we are thinking we are using discrete basis. And we have another cavity here. And this cavity is originally resonant to only 4 red photons. So orange photons stays in this cavity. And these red photons coming to here. And at the moment, we are using APDs. And this D is like this. Almost transparent beam splitter and very, very weak coherent beam. And here we have a APD like this. And we have a click here. This APD cannot distinguish between the photon coming this way or that way. So by using entanglement, we can create superposition of 0 and 1 here. And we have 3 of them. That means we can create arbitrary superposition up to 3 photons. And also, we did creation experiment like cubic phase state and bigger cat state and three-headed cat state. And we already succeeded in memory experiment. Importantly, we can memorize phase information. Usually, quantum memory memorize only single photon, something like that. In that case, that type of memories cannot memorize phase information. But in our case, we can memorize. Oops.
Akira, if I can
phasing-
just jump in real briefly, there's 5 minutes left. I don't know if you saw me
Alright.
last time. Thanks.
Phase information like this. So we can memorize, create and memorize this type of state. But at the moment, we are using APDs, but we are now developing photon number resolving detectors. This is our photon number resolving detector result. We can count photons like this. All right. A little bit early, but this is my final slide. Let me summarize my talk. We can make large-scale entanglement by using only 4 squeeze vacuum and 5 beam splitters and 2 delay lines. And by using ancillary input, we can make pi over 8 gate. Of course, there are 2 paths. One is use cubic phase gate. Another path is use magic state. But in both cases, we can use same gate teleportation setup. And we can make fault tolerant by using GKP qubit. Thank you for attention.
All right. Thank you, Akira. So we have, it was 2 minutes early, so we have 7 minutes for questions. There's one question in the chat, and we can start with that. If people have questions, please go ahead and ask it. I'm going to read out the question so that everyone knows what we're asking. So the question is from Gan Beng Yi. Please forgive me if I mispronounced your name. Can the issue about large-scale optical circuit be solved by considering integrated quantum photonics? If yes, what will the limitation factors be when using integrated quantum photonics? Thanks.
All right. So in the case of electrical circuit and classical computers, nowadays transistor size, line space of lithography is something like 10 nanometers. That's why you can use many transistors in a very small chip. But in the case of optics, we have our wavelength is very long compared to 10 nanometers. So we have a diffraction limit. That is almost wavelength. And in that case, our device size is at more the size limit, small size limit would be 1 micron. So that is 100. No, that is at least 100 times bigger than transistor size. So integrated circuit in that sense does not work. for quantum computers. So in any case, we have to use time domain multiplexing. Otherwise, we cannot use large scale. That is my answer.
Okay, great. Thank you. So we have a question from Rajveer. Rajveer says, great talk. What is the role of the displacement operations right before the heralding in your quantum memory experiment?
Oh, let's see. Okay.
Yeah.
The question is this one, right? This displacement,
I believe so.
right? Okay. So as I told you before, so we want to have superposition state. And if we don't have this beam splitter, I mean, we don't have this displacement. This is just yes or no. So just single photon or no. But we need superposition. So we have to make some trick to make superposition. That is this displacement. I mean, as I told you before, this APD cannot distinguish the photon coming this way or that way. That's why if the photon coming this way, it means we are looking at this photon. So in the cavity, we should have this orange photon in the cavity. But in the case of the photon coming this way, that means there is no photon in this path. So that means there is no photon. So the case is 0. That's why by using one click, we can make superposition this one and this one, right? Okay.
Right. So it's, I see. So it helps to, yeah, okay, helps create state. Let's see. I'm going to take a question from Barbara Terhall. Barbara asked, do you have an idea of how good a GKP0 state you would create in terms of effective squeezing, delta, or some other measure?
That is a very tough question. Honestly speaking, I don't know at the moment.
Okay. All right. Short and sweet. There's one more question. So this is by, oh, I'm very sorry about your name. Subhashish Parekh. Can you use this quantum memory for creating any type of non-Gaussian states? What's the limitation or main challenge to this heralding-based quantum memory?
So of course, this part. I mean, so simple superposition state. In the case of simple superposition state, this setup is very simple. But if we have to create very complicated non-Gaussian state, we don't know how to use this phase or this one, and so how many photons we should detect and so on. So that's why Xanadu people are using to determine the condition with AI. So it is not straightforward to determine how to make this type of setup. It is not trivial.